Good day, folks. This is a short video on chapter 13 and page number 668 and chapter 13.4, and the questions are on the topic of Snell's law. Snell's law. That's what we're gonna cover in this video. So I'm gonna first of all write the formula for the Snell's law. It is n1 sine of theta 1 equal to n2 sine of theta 2. And with that, I will also describe what does the Snell law says, that if the light is incident on, oh, okay, this is the law of refraction first of all before getting into the Snell's law. So the law of refraction says that if the light is incident at an angle theta with normal and it enters from the rarer medium, let's say this is air, to a denser medium, which is water, then it will bend towards the normal line. So this is the normal line, normal, and this angle will be theta 2. And when the light goes from the denser medium towards the rarer medium, this is the denser, this is the rarer medium, it will bend away from the normal line. So this is the normal. This would have been the ideal path, but it bend away from the normal when it moves from the denser to the rarer medium. That's in accordance with the law of refraction. Now, Snell law says that if I multiply the refractive index with the sine of theta 1, that should be equal to the n2 sine theta 2. Means refractive index of the material 1 multiplied by the angle of incidence with at an angle with the sine of that is equal to the n2 multiplied by the sine theta 2 in the other medium. And what is n? N is the refractive index. And we've already talked about the refractive index. I'll quickly tell you one more time what refractive index means. This means the uh, speed speed of light in vacuum divided by speed of light in the given medium. And refractive index will always be greater than 1 because speed of light in vacuum is the highest. Nothing can be more than that. All right, now just let me quickly check if it is being recorded or not. Yes, it is being recorded. And going back to the topic, I'll take a question, as I said, from page 668, and I'm going to take the example number 13.3. And before I jump into that, I will cover another formula. So the formula is, well, my apologies, I'm not taking example 13.3, I'm taking example 13.4, which is on page 670 first of all. Okay, now the formula is on top of that example which is given to you. That is sine of theta 1 upon sine of theta 2 equal to v1 upon v2 equal to lambda 1 upon lambda 2 equal to n2 upon n1. This formula is given to you on your formula booklet also. This formula came from, basically this is Snell's law. So if I look at this one, what did I say? N1 sine theta 1 equal to n2 sine theta 2. That's what I said. Now if I rearrange the terms, I can write it as n2 this divided by n1, here n1, and cancels out. I can write it sine theta 1 equal to n2 upon n1 and sine of theta 2, and this sine theta 2 gonna go on the bottom of the first term. I can write it as sine theta 1 upon sine theta 2 equal to n2 upon n1. So this two makes the Snell's law. And now from where the velocity and the wavelengths are coming, so this is, if you break down these n2 and n1, because n2 and n1 are the refractive index. Refractive index tells us about the speed of the light. From there the speed comes into the picture, and then we talk about the speed. Then speed is also equal to frequency times lambda, and from there this comes into the picture. I'm not going to get into the detail of this one because this formula is already given to you and you don't need to solve this formula. I just wanted to tell you from where these terms are coming along. All right, so now let's go to the example. Example 13.4, in which you are given a ray of yellow light with the wavelength lambda is given to you 570 nanometer. Nanometer means 10 to the power of -9. So now you can always ask me the question, hey, hang on, in the book it says that 5.70 times 10 raised to power -7. Don't confuse yourself. I am saying 570 times 10 to the -9. The book has moved it into the scientific form by moving this to the two decimal to the left, and they've written it in this format. So both are correct. And wavelength is given to me 570 nanometer, and travels from air into the diamond, from air to diamond. And one thing, if you are asked a question like this, you will be given the refractive index in the question. So air has a refractive index of 1.0003. Diamond has the refractive index of 2.42, if I'm not mistaken. Yes. And we wanted to find the speed of light in the diamond. And the angle, it also tells me that uh, angle is 30 degrees. So I mean the speed of light uh, from travels into the diamond at an angle of 30. So angle of incidence, always make the diagram for these kind of a question. This is 30-degree angle. So I will write it as n1 sine of theta 1 equal to n2 sine of theta 2, if I'm looking for the theta 2 angle. But I'm not looking for theta 2. What I'm looking for is the speed of light. Speed of light. So I know the n1 and n2 values from this formula. These two are given to me. I need to find the speed of light in the diamond, and speed of light in vacuum or air, we can take it as 3 times 10 raised to the power 8 meters per second. And this is given to you in your formula booklet also. With the on top right corner you can find this one. If the book also says 2.98 times 10 raised to power 8, which means one and the same thing, which whatever number you want to use, you can use that number. Now I can write the formula n2 upon n1 equal to v1 upon v2, and n2 is diamond, so because it goes from air to diamond, so that's how it is. As I told you, make sure you always write the formula theta 2, and n2 is diamond, so 2.42. This is 1.0003, so 1.0003, and this is 2.42 equal to v1, which is the speed of light in air, 3 times 10 raised to the power 8. V2 value we have to find out. When you're going to do the cross multiply, you're going to get the v2 value from here. That will come out to be 1.24 times 10 raised to the power 8 meters per second. So once we have the velocity, we can compare now the wavelengths also. So if I compare the wavelengths, lambda 1 upon lambda 2 equal to n2 upon n1. You could have compared n1 lambda 1 upon lambda 2 equal to v1 upon v2. You could have done either this one or this one. Both will lead to the same answer for you. Now in this one, if I put in the value, lambda 1, which is incident light, is 5.70 times 10 raised to power -7, and divided by lambda 2, which I am looking for. The wavelength of light, yeah, in air is this much, and n2 is 2.42 divided by 1.0003. Again, I'll cross multiply. Lambda 2 will go on the other side, 2.42 lambda 2, 5.70 times 10 raised to power negative 7 multiplied by 1.0003, and then dividing both sides by 2.42. 2.42 cancels out. Lambda 2 value I can easily find out from here, that is 2.36. 2.36 times 10 raised to power negative 7, which is 236 nanometer also, right? So that's how you're going to solve this question. So the idea about these questions, the trick to solve these questions is always remember to draw the diagram. And please make sure you guys do the question from 673, critical angle. So I'll just quickly tell you, critical angle is that angle at which angle of refraction is 90 degree. Again, angle of refraction is 90 degree, means no light comes out of the given medium, and this is how the light travels on the surface. It stays on the surface. So angle of refraction means light starting from inside the denser medium and it stays on the surface. Angle of refraction becomes 90 degree. The So if you are asked to find the critical angle, angle of refraction is always 90 degree, and you have to find this theta angle. And one more thing, once you go beyond this critical angle, that will be a case of total internal reflection. Total internal reflection, theta 1 will become theta 2 once you go beyond that. And based on this principle, fiber optics work. Fiber optics or submarines also under sea, they see based on this principle. So that's it from my side, and I'll see you with another video. Till then,